So let's begin. For a quick agenda, this is what we're going to be going over, how autonomous vehicles have evolved from a completely manual drive to something much more automated. Then we'll dive into DDS, what is DDS, ROS2, and how to get started. Okay, first, evolution of vehicles. So back in the olden days, everything was manually driven with vehicles, and there wasn't a whole lot of automation available. As electrical systems were added to vehicles, there were things like point-to-point wiring, and then it was got to be shared buses and shared memory until finally networks were added to it. But this chart, as you look at it, imagine it downwards is going forward in time, and levels of autonomy is increasing, and the number of sensors is increasing. And of course, the amount of communications and the amount of data that's being generated keeps increasing, and more processing gets added. So a vehicle had to go from simple wiring to buses to networks, and even on to something more sophisticated. So today, an autonomous vehicle might look something like this, where you've got multiple cameras, radar, LiDAR, GPS, and IMU, mapping, compass, all kinds of sensors. And since people's lives depend on it, it needs to be, it's got a lot of requirements on it for low latency, high throughput, reliable communications, etc. What it's doing, though, is it's generating a whole lot of data. And this is a chart that came from a study by Stanford University, looking at the different types of data that's available in a modern vehicle. The point of this article was that just by the amount of data, that 5G is not going to solve the problem. This data is not going to be processed in the cloud. It's going to have to be done on the vehicle. The clear thing is that autonomous vehicles need lots and lots of data flow. And this data flow isn't, it comes in lots of sizes and shapes, different types of streams of data. Some of it is high volume but low frequency. Some of it is the opposite, and there's a mix of everything in between. By these different data flows, some of them have to be absolutely reliable, and others you can drop packets. It's not a big deal. What's clear, though, is it needs a really wide range of quality of service for the delivery of this data flow. What would be ideal is if you had a single technology that could handle this rather than cobbling something together piecemeal. So we took a quick look at how autonomous vehicles have evolved through the years. Let's do the same for networking and see how that matches up with our needs. All right, so back in the early days, everything was point to point. If anybody has taken any kind of networking programming, it's very easy to open up a TCP socket or a UDP socket and make a simple point to point connection. This evolved to a client server or broker based. Also, going forward, it's things like CAN bus or some IP were available that make things a little bit easier. There's also another approach is queuing services, where you can have multiple subscribers onto a single point and data gets queued and organized. But what's wrong with all of these technologies is they're all focused on messages. The data is really only an afterthought. It's like the payload that gets carried through on the system. What we found is that focusing on the data and making more of a data-centric architecture really frees up a lot of things in creating a modern networking solution. And for autonomous vehicles, RTI has been pretty successful in this. We are the primary creator of DDS. It's been used now in over 200 autonomous vehicles of all types. Passenger vehicles, things that go under the sea, under the ground, in the air, out in space, all types, a lot of research applications. And what we're finding with these large systems is they will typically, and this happens organically a lot of times, they will evolve into a connectivity framework that looks something like this. And this is an example of what a connectivity framework looks like in an autonomous vehicle, where you've got cameras and LiDAR and mapping, and it ends up making this sort of layered or tiered data bus architecture that anything can connect to. It's got discovery built in, and it really adds a lot of flexibility for things, because it's very easy to start in one position and continue and to evolve forward, adding things to the system as needed. So taking a look at that, say if you were to start out with something pretty basic on an autonomous vehicle, where you've got some sensors, some sensor fusion, some basic path planning, you've got manual control of the vehicle. This might be a class 2 or class 3 or level 2 or level 3 autonomy vehicle. And then as a vehicle designer and manufacturer, maybe in the future, you might want to add components that conform to the AUTOSAR adaptive standard. AUTOSAR adaptive is also based on top of DDS. That's one of its supported transports. So it's very easy to patch in a DDS system to another DDS system. CAN bus is something that's used a lot in automotive today. It's very easy to, since CAN bus is a publish subscribe protocol, it's very easy to gateway CAN into a Connext DDS data bus. Similar for ROS2. There's a whole ecosystem of ROS components. ROS2 was designed and built on top of DDS. So it's very easy to add that in. And finally, in the area of large-scale simulation and hardware-in-the-loop testing and validation, DDS is used extensively because of its huge data carrying capabilities, low latency, quality of service. So as a vehicle manufacturer, it becomes very easy to start with what's considered a pretty contemporary autonomous vehicle design now that has lots of sensors, and they're integrated in a single centralized place. You know what's going to happen with technology. They're going to go towards things like integrated radar and camera and LiDAR that have processing integrated as well. Using a data-centric approach makes it where it's really easy to take the software that was centralized and distribute it without having to rewrite the whole thing. So it's very convenient that way. Who else is using DDS? Right now, DDS is core to more than a dozen standards and consortia efforts. I mentioned ROS and AUTOSAR, but it's also used in modernization of the grid, AV controls, hospital automation, and this doesn't even include some of the internal standards that customers have used who have standardized on DDS. For example, the United States Navy, their entire surface fleet is running on DDS, every ship that's on the ocean. Let's take a look at a few examples really quick that are kind of interesting. Flying cars or air taxi services. Airbus is one of our customers that's put together what's essentially a flying taxi that runs on DDS. And it can do things like avoid birds and work with local ground control radar to navigate correctly. Speaking of which, if you want to have unmanned vehicles or automated vehicles flying in national airspace, it's good to have the airspace infrastructure working with it. This is another use case for DDS. This was the first place that that DDS had been certified or safety certified to a DO178C level A, which is an FAA standard. It's a very stringent standard for safety for software systems. Let's go to the opposite extreme for another example. And this is deep under the ocean. One of our customers is using DDS for providing telepresence at great depths. So rather than sending out a diver or a submersible, the maintenance technician, and this is typically for oil rigs, can essentially use a telepresence robot and stay safely in the ship and be down to depths of up to 4,000 meters. For those who are into space, the Kennedy Launch Center complex in Florida is the largest single control SCADA system in the world. Huge amounts of data, and that's all running on DDS. It's 300,000 points, 400,000 messages per second. What's interesting about this application is not only is DDS used in the launch complex, it's also used in the in-flight monitoring, the UAV reentry, and also the ship that retrieves the returning spacecraft is running on DDS. So it's kind of a neat full circle picture here. Grid modernization, we're using lots of power grid projects. The largest power plant in North America is running entirely on Connext DDS. So let's take a look at what DDS actually is. Now, what DDS is, it's an open standard, which is kind of a neat thing. It's managed by the OMG, or Object Management Group. It's actually covers 3 areas of the standard. It covers at least 3 areas. Looking at the boxes on the right, on the top end, the standard covers the DDS software API. It makes it where if you write your application to the standardized DDS API, you can then change DDS vendors with just a simple relink or of your application. Or if you're using dynamic libraries, it doesn't even need a relink, just switch libraries. On the bottom end, there is a wire protocol. It's called real-time publish subscribe. That makes it where different providers of DDS can all interoperate with each other. In fact, there's annual plug fests held for the DDS makers. As new additions are added to the spec, the DDS vendors will get together and have a plug fest to make sure that everything interoperates. And then on the side of the box, the standard defines a plug-in security architecture. That makes it where it's really easy to add or upgrade security, encryption, authentication, access control to DDS, and it's defined by the standard. DDS takes a slightly different approach to security. It doesn't secure the pipe. It secures the data payload, and it does it on an individual item basis. Anyway, DDS is available for multiple language bindings. You pretty much find DDS available for whatever your favorite language is, and it's available on almost any platform, including bare metal embedded. So I said DDS is a standard. It's actually a family of standards. So it defines how to map DDS to different languages, or how to map it to a web services, or to OPC UA for those that are into factory automation. There's even a XRCE spec that is for an extreme resource constrained environment. For something like a microcontroller, it can actually operate in a DDS environment. Last night I went to the OMG website. This is one of the cool things about the DDS standard. It is a completely open standard. This is the list of available standard documents. Looking at the adoption dates, they're all pretty recent. It's a very active community. It's not like it's this static standard. And just a note on the difference between open standard and open source. Open standard is in a lot of ways more powerful than an open source implementation. For example, Linux is open source. That means that they can change it in any way they want, and anybody else that wants to make their own Linux would have to then follow it and use the code itself as a standard. But an open standard means that anybody can download the standard and make their own implementation. As of today, there's about a dozen implementations of DDS, both commercially supported and open source. It's about 50-50 of each. Let's move on. So again, some of the highlights of DDS. One is that it's data-centric, which is it's very liberating for as a software developer to only deal with the data and not how to get it to different places. As a standard for data transmission, it's really high performant, really efficient. It does not need to stringify the data as XML or JSON. It only sends the data. It sends it in this compact and very efficient binary data representation. Compression is available as well. It has an automated discovery process by which you can discover peers. It's also transport independent. So you can write your code and maybe it's talking over a UDP network, but in the future you decide that 2 different nodes can exist on the same computer, and it'll automatically discover that there's a shared memory segment in between them and be able to use that for communications and really up your efficiency that way. But one of the most powerful things about DDS is that it has a really rich set of quality of service options. And that looks something like this. This is a summary view of things. So there are, like if you're sending large packets, it'll break it up into smaller ones and publish them asynchronously. That's down in the bottom corner. If you've got a lot of small packets, it will batch them together. It's got its own reliability mechanism. It's got ways of dealing with late joiners. It can do filtering based on time or on content. There's just about every real world networking problem that you could encounter. There is probably a quality of service setting available in DDS. That is its greatest strength. It also can be a challenge sometimes for those that are working in a very constrained or challenging environment. it requires a bit of knowledge about the quality of service settings. One of the things that RTI has done to make it a bit easier is to use QoS profiles for common applications. So with a single line of specification in a QoS spec file, it's possible to set it up to say, okay, this is going to be for streaming sensor data or image data, or this is an alarm, and I want to make sure that I know it's alive, but it's rarely, if ever, going to be triggered. So let's take a look at what DDS actually does, and this is in the area of data communications. So as a software developer, you may start out with structured data. I mean, this looks like a C structure, and this is the kind of thing that that DDS works with. If you wanted to get it to a different location, ideally it would be some invisible process that just works, and in your destination the data just appears. I mean, wouldn't that be ideal? Or maybe it's going to multiple destinations. It would be really cool if it just worked. And you didn't have to deal with messages or with addresses or with routing or brokers or anything like that. Wouldn't it be great if that just worked? So imagine you're putting together a distributed system, like an autonomous vehicle that has lots of processing nodes. And it would start out getting a little lag on the computer. So the system, imagine each one of these blue boxes is a processing node or an application function. And it could be, in the initial days, it's very tempting to just open up a socket connection and do a direct point-to-point. You know where the data needs to go. The trouble with that is, though, while it's easy and convenient, if your system needs to change or evolve and you start adding things, not only do you have to do that work, but often you have to go back and touch everything that touches that code to add in the new consumers and producers of data. So it's very brittle, even though it's very convenient. This is an example of the slippery slope of middleware, where it seems in the early days like it's easy to do a middleware, but when it actually gets to real world conditions, designing middleware is hard. And we'll touch on that a little bit later in the presentation when we start talking about ROS. Let's see. So, and the other thing is, in doing this, this is an example of some of the things that are missing. How are things going to discover each other? How do you secure the data? If you want to use a different programming language or have a new platform, how do you handle doing all these things? Real world middleware it's hard. Okay, so one of the ideas that's come along is the idea of using a central broker. So this makes things a lot easier. If you have every application just talking to a central broker, and internet is a good example of that, where there's websites that clients talk to, and that's how things get done. So the pluses are it's pretty easy to use and it's a consistent interface. In a safety critical system, the bad part is that for one, it's a performance bottleneck. Everything has to go through the broker. For two, it's a single point of failure. So if your broker goes down or your central server, then your whole system is down. This makes scalability difficult, and oftentimes this central server is the single most expensive piece of equipment and also the most failure prone and most brittle in your system. So it does have its place, but for something that's critical, it's really not that great of a choice. So what DDS creates is this idea of a virtualized data bus that is transport independent. So it might look something like this in a system diagram. And you're dealing again with data topics because it's a data-centric approach. And imagine that the blue node in the upper left corner has this data, and another one of the boxes wants this data. Well, through a discovery process, it's found that the data had, the published data matches the data that they want to subscribe to, and a connection is made. This is what happens underneath the hood after discovery. And what's interesting is the underlying connection is a point-to-point connection. So it's really efficient this way. If they're on the same machine, it'll be done over shared memory. It could be across a backplane, over serial bus, over a radio link. It's whatever the results of the discovery process finds, it will automatically make that connection for you. So this is something you don't have to deal with in your code. All you need to worry about is the data itself. If there are multiple subscribers to the data, then they'll just be added and no changes need to be made to the code. This is kind of cool because as your system evolves, if one of these new nodes needs this data, it just gets added and published to the data. So imagine if this were on a UDP system or using UDP networking, this particular one where you've got one publisher and 4 subscribers, it might be done over UDP multicast. And we can do that reliably and securely, even though UDP is a unreliable and unsecure network. So what DDS is doing is it's taking the best ideas from broker-based systems and the efficiency of a point-to-point connection, combining them by putting some of this logic within the library itself that gets embedded into each participant onto a DDS data bus. So this becomes really liberating for a software engineer to be able to write code that only deals with the data and doesn't worry at all about how it gets there. So it makes for really nice loose coupling between systems, but at the same time, really high performance. So let's take a look inside one of the application modules and see what DDS is doing internally. So here we're zoomed in on one of the blue boxes. And at the heart of a DDS system is what's called a domain participant. Now this is a bit of a heavyweight process where it's creating multiple threads. It does a bunch of memory allocation for its needs depending on its configuration. And this is the entity that handles discovery and creating publishers and subscribers and topics. And usually there is only one per application. So it tends to be a shared resource because of its, the amount of threads and memory that it requires. Now, in here, it's mentioning that it participates in a single domain only. And what a domain is in the DDS world, it's just an abstraction that partitions a network or a data bus into different segments. This is done by number. So it'll be numbered from 1 to about 248, I think, are the number of domains that you can have. And this is a logical separation, even though they're sharing the same hardware or same network. Applications that are on different domains cannot speak to each other. So inside a domain participant, as I'd mentioned earlier, there are publishers and subscribers, and they will make data readers and data writers that will write or read topics. And to facilitate some of the operations, there's a few buffers that are made. There's a transmit buffer for the publisher and a couple of buffers for the subscriber. And this again works on topics. So this leads really well into a quick discussion on DDS reliability and some of the features. And I'm going over this more as it's like a map of the forest, where if you start implementing your system using DDS, it will be easier to know, oh yes, there is a reliability mechanism, there is a persistence, there is a failover mechanism, that sort of thing. Let's take a look at DDS reliability. So we're back to the same diagram, looking at the buffer diagrams here. So imagine I'm sending a packet. So here's a sample of data. It's sample number 1, and it gets sent over the network and received by the receiving application. Now this first sample, all samples are numbered. And so it'll be looked at by the receive buffer and say, okay, this is the first sample. It's not out of order. So it'll go directly through the receive buffer and be available to the application. So this continues, sample 2 gets sent and put to the application. Then there's sample 3 and sample 4. And for a reliability mechanism, DDS has what's called a heartbeat. And this is really a request for acknowledgement. And this is sent periodically. And one thing to note about DDS is everything is adjustable. So it makes for a lot of granularity in your tuning capabilities for network performance and getting just the right performance that you need. Out of the box, it works really well. The default settings make it where it works great in most common networking applications. So in response to the heartbeat, the application is going to send an acknowledgement that says, I received samples 1 through 4, and it's only at that time that they can be retired from the send buffer. So, and things get retired from the send buffer when we're talking about strict reliability, and there's lots of grades of reliability. So this is a 1 publisher, 1 subscriber, but things will be retired only when all subscribers that are subscribing reliably have acknowledged they've received all samples. So this will continue with samples 5, 6, 7. The heartbeat or request for acknowledgement can be coupled with samples. And so then it'll be acknowledged and then retired. So settings for everything, you can set different rates for sending heartbeats. It can be done based on time or on number of samples. There is specific settings for what happens when you get a late joiner to the network that needs to catch up. And pretty much everything is adjustable. So it's very, very powerful that way. Let's take a look at what happens when you get a drop sample. Suppose sample 2 got dropped from that scenario. What would happen is sample 1 would be available to the application buffer, but samples 3 and 4, since 2 was dropped, would be sitting still in the receive buffer. So when the heartbeat comes, it acknowledges I only received 1, 3, and 4. So those can be retired from the send buffer. And say it was already busy sending sample 5, it'll then do a repair packet to send sample 2. And then at that time, samples 2, 3, 4, and 5 are available to the application. So it can guarantee that you get in-order reception of all packets this way. Nothing is received out of order. Again, it's just a convenience for the software engineer that you only have to deal with the data. You don't have to worry about the transports. So there's a lot of code that you don't have to write in using DDS. So that'll continue sample 7, sample 8 with the heartbeat, and then it'll acknowledge that it received 2 and 5 through 8. And only at that time do things get removed from the send buffer. So imagine now that you have something that's a very low, a low update rate, and it's a combined sample and heartbeat. So we've got sample 1 plus a heartbeat, and that one was dropped. So the sender says, hey, I didn't get an acknowledgement. So we'll ask for another acknowledgement with a heartbeat. And the receiving application will say negative acknowledgement. I did not receive it. And then the sample will be resent and it can be acknowledged again. So this allows for some really interesting things. So UDP is as I said before, UDP is it's a transport that doesn't have a reliability mechanism, but it does allow multicast where you can publish a single time and it'll be received by multiple participants. With this mechanism, since DDS has its own reliability mechanism you can actually publish reliable data to multiple subscribers on multicast. So it publishes it on multicast, the acknowledgements come back on unicast, and if there's any republications that need to be done, that's on unicast as well, where unicast is sending to a specific location, not to multiple locations through a multicast. What's also kind of interesting is this was all going over a protocol level reliability, but you can even kick that up to the application level for application level acknowledgement. Imagine you have a system that is issuing over a DDS network a firmware update. So you don't necessarily want to know that the application received the update. You want to know that it applied the update. So you can do an application level where it's up to the application to send the acknowledgement. It says, yes, I've received it, I've verified it, I've burned it into Flash, I've checked it, it's good, you can now delete it from the send buffer. So it's really powerful. We see that a lot in military systems where there's things like mission plans that are large files and they don't want to be resent or redone multiple times. So they needed to know absolutely that it's been received and processed. Okay, so while we're on the topic of buffers, you can do a lot of things just because you have this buffer mechanism for reliability, and that's implementing some history and also a durability mechanism. So for the application, having a history buffer is kind of convenient. You've got now this history that says, okay, I've set it up to have 10 samples, and I've got a history of the last 10 samples that I've sent or received. What's kind of interesting about that as well is that when you get a late joiner to the system, say if you have an application module and it was reset or it just takes longer to start up and it joins the system and it's subscribed reliably and it has a history buffer of 20. What it'll do is it doesn't have to wait for the next send of the data that it's interested in. It will immediately receive whatever the sender can send. So if there are 10 samples in its history buffer, it'll receive the last 10. We see this a lot for things like status. Typically, the history is something that has the last published value. So if there's a late joiner to the network and wants to know immediately what the conditions are in the system, then it gets that right away. It doesn't have to wait for the next interval. So that's something that's called durability. And there's different ways of doing durability. The settings that are available in DDS, one is volatile, where there is no durability, so there's no history buffer. One is called transient local. You'll see these things in the quality of service settings file if you want to do anything with like late joiners. This is what they mean. A transient local is one where the history is kept in the memory of the publishing application. If you see one that's called transient, that means it's using a separate service that does this for the system. So it will subscribe to whatever topics you tell it to subscribe to and make them available as a durable source of data. And then the last one is persistent, where it'll do that, but it'll also spool it to disk. So the last state of the system can persist across reboots and power cycles, which is kind of cool. Now let's take a look a little bit closer into DDS topics. Okay, so we have different topic data types, and as I said before, it is just structured data. So the first one is to use strongly typed data, where if you look at the data types used in these structures, they're pretty conventional. Long, float, int, string. What's convenient about these is DDS has support for filtering by topic, but only for strongly typed data types. If it's some user-defined type, then it can't do it. So it allows a lot of flexibility, and we'll get to that in just a second. The other type is loosely typed, where say you see up on the top, it says that this is a string and that data is just stringified XML or JSON data, which is really flexible. It makes it where you can put any payload in there, but it's not quite as fast, and it doesn't take advantage of what DDS can do with data. But sometimes you need this sort of data because your data is so fluid and flexible. The other option, of course, is to mix the types, where you're using some strongly typed data and some stringified data. Now, you may have noticed that in some of these topic definitions, there's this indicator that says @key. And what this is, it is a feature of DDS that allows you to designate elements as a identifier. So it's similar to a key in a database. What you would put in here is a unique identifier that this publisher, to identify the publisher of the data. So for instance, if I had 100 different temperature sensors on the vehicle, all publishing data, I'd make it to where they all use the same data type, but they have a unique identifier in the form of a key. What's interesting about that is I can then subscribe to, without using keyed instances, I can subscribe to all of them and then just use the key identifier to know which one it's coming from. Or I can do a specific instance subscription that says I only want data from this one particular publisher. And that'll make it where that particular publisher is the only one that I receive data from. I receive it from no others. So looking at the filtering capabilities, if I'm using a strongly typed value, and let's use a temperature sensor again, imagine that I have a temperature sensor, but I only want data from it if its temperature gets over 180 degrees, Fahrenheit, or 80 degrees C, or something like that. DDS supports, and these supports doing this, where the filtering parameters are actually pushed to the publisher, where the publisher won't even send data if it doesn't match the filtering requests of any subscriber. So it does a great job of keeping data that you're not particularly interested in off of the network. So really efficient that way, rather than having your subscriber get all the data and have to do the filtering itself or by itself. What's cool about this also is these filters can be changed on the fly. So if you're in a different condition, you can change the filtering thresholds for when data is allowed to get through. All right, another powerful feature that's within DDS is this idea of data type extensibility. Okay, so there's 3 different types of extensibility, and extensibility just allows you to add elements to your data types. So the first one is final type, and this is one where this is the final type. You can't change it. It's a good example of when this is good is if you're implementing something that conforms to a standard, for instance, and you don't want any users, any of your developers adding a data type to it. Okay, the second is extensible type, And this is the default for RTI Connext. This makes it where you can add, append at the end of the structure new elements, but it retains forward and backwards compatibility with the earlier type definitions. So it's really convenient. If anybody's done any kind of data modeling, it's hard to get it right the first time. You do your best, and then some new condition comes up that says, oh no, I have to change and add values to it. This makes it where it still works in both forward and backwards directions. And the third one is what's called mutable type. And that's where you can pretty much make whatever values you want within a structure. It will just, at runtime, figure out what the positions are. So it's completely fluid using mutable type. And the reason why it's not used all the time is, yes, it's flexible, but it also means that you have to send the type information and position information with every packet. So the receiving end can figure out which data is which. With the other two types, the position and type information is only exchanged once at discovery, and then it's just the values that get sent during each data packet sample. Okay, so when data is sent, the topics have some attributes. There's a chunk of metadata that comes with every sample. So the first one is that every sample is timestamped. It's timestamped when it's published and when it's subscribed to. And this enables a lot of really cool features. One is that you can do time-based filtering. So for instance, if I had an RPM sensor and I could publish data from it at up to 100 times a second. So imagine now I have a subscriber that only wants 2 samples per second. I could subscribe, you would think normally I would subscribe to it, I'd get 100 per second, I'd have to manually filter it out. DDS supports the idea of time-based filtering, where instead of getting a new sample every 10 milliseconds, I only get the ones every 500 milliseconds, and it's the closest sample to that 500 millisecond interval. This also lets me set the lifespan of samples. This would be a way of saying, as a subscriber, I'm interested in this data, but if it's more than 10 milliseconds old, I don't want it. And so my application won't even see it then because it exceeded its lifespan. There is also a callback available that says, okay, you're getting packets that are past their lifespan, and I can use that callback if I want. Another thing that's interesting is normally if I have multiple publishers and one subscriber, the data is presented in the order that it's received. But now imagine that I have a system-wide clock that is synchronizing all my sources. I can actually enforce publication order reception from lots of different publishers. So for instance, if I have a publisher that's on shared memory with my process and others that are going over a network connection, then I will receive the samples in the order that they were published, even though I'm actually receiving some much quicker than others. The other one is ownership and strength. So this is a way of allowing for redundancy in the system, or to be able to do system upgrades with no downtime at all. So imagine you've got a strength rating on a publisher. So it's a numerical rating. Say I have a publisher that is at strength 10, and I've got another one that's at strength 20. And if I'm looking at exclusive ownership, then I will only listen to the one with the higher strength. If I was doing a planned upgrade, for instance, and I came in with one with a strength of 21, then I would automatically switch over. So you could actually do things like, imagine you're in a race condition and a camera goes out. You could actually, while the car is running around the track, switch over and install a new camera, or switch over to a new camera just by turning it on or plugging it in, if it's at a higher strength, and you'll get no system downtime. So a very cool thing to have. All right, so let's take a couple of minutes and talk about the discovery process. So looking at the DDS data bus, imagine I've got a couple of participants and they're already running, and a new participant comes online. Discovery is a two-step process. The first process is this new participant will announce itself with a participant discovery message, and this is done to its initial peers list. This is the default initial peers list, and by default it uses loopback on UDP. It uses the local host. connection also on UDP and shared memory. If I wanted to talk specifically in its discovery list to specific IP addresses, I could also put them in here. So what it's doing is it's saying a little bit about itself. It's, here's the transport I'm on, here's my unique ID, here's how you reach me, and a little bit about the quality of service settings. Anyone who receives this announcement will respond with an endpoint discovery message. And this is, here's how you reach me, here's my data readers and writers, my topics, my data type names, and my quality of service settings. If you find publications that have the same data type, the same topic, and a compatible QoS, then a match is made and a connection will be made between them. And that's the discovery process. It happens, one question that comes up is, how long does discovery take? Well, it happens very quickly, but it repeats about every 30 seconds. So you can tell, if there's no liveliness mechanism in place, you can tell if something has dropped from the system within about 30 seconds. But if you're using something called liveliness, you can make that interval much more quick. By the way, this discovery information, it does enable a lot of really great tools. This is just a quick view. We're going to look at this a little bit later of one of the tools that's available, that's in the tool suite that all the participants in the IAC are getting from RTI. This is called Admin Console. What's neat about this is using just discovery information, I can see all the topics, all the participants, and immediately see if there is any kind of QoS or data type mismatch problem. This is such a go-to tool. I can't count the hours, how many hours this has saved me just having this one tool. We have lots of customers that are just leaving this tool running all the time because it is so useful. Okay, so we've learned a little bit about how DDS gets used. Let's look at some of the design patterns that are put in place when you've got a pub-sub type application. Okay, so we talked about publish and subscribe. All right, one publisher, many subscribers, or a single subscriber. Imagine you take two topics and put them in each direction and put them in a what's more like a request-reply pattern. So this is a way of, even though you're a data-centric approach, you can trigger actions like a remote procedure call. Let's take that a little bit further. Now imagine you've got multiple requests and multiple replies and you need to correlate them with each other. There is a message identifier that helps you correlate which reply goes with which request. Or the pattern might be where you send a single request and there's multiple replies. That's all possible. Or a single request to multiple repliers. This is a pattern that's really interesting. Imagine you have a radio connected source that you want to get data from reliably. So you can't exactly send an ACK back over a radio if it's a one-way link. So that publisher over a radio link is essentially just sending, and it's doing it with best effort and reliability mechanisms. But then you use a persistence service and make that be your source of reliable data. And you can then implement an application level acknowledgement or something that just wants simple durability, but it's a way of getting the data reliably from a very unreliable publisher to your application or your system. Okay, so I wanted to mention that there is a Q&A window as well if anybody needs to type any questions in. And I will be covering a resource list at the end where there's forums available for questions about DDS. But let's take a quick look at ROS. And I'm going on the assumption now that most of the attendees here are already familiar with ROS. This is a statement from the ROS website, and it says what it is. So I won't dwell too much on ROS if I'm expecting that most people are familiar with it. But briefly, it's not an operating system, even though it's called Robot Operating System. It is a framework for creating robotics applications. It was created for and by researchers and robotics educators. There's probably more than 1 million computer science grads that have been trained on ROS, so there's a huge pool of people that are trained on ROS. And it has a lot of capabilities. One of the things that was learned in ROS, though, is the value and power of ROS is in its tools and the capabilities and its vibrant ecosystem. A lot of really great things in there. The plumbing part of it, and this is speaking of the original ROS 1, was the thing that was holding the original ROS back. And this is something that Open Robotics themselves have said about, doing middleware is really hard. With the original ROS 1, they made their own middleware. This is what the architecture of the original ROS looks like. And it's got their own implemented middleware. One of the other issues is there is a master node that facilitates discovery and a global parameter system. So it's something that it's great for research. You can have lots of hands-on capabilities for modifying things, but it's not suitable for a commercial or mission critical or safety critical application. It doesn't scale well. It's not, and it wasn't written to be deterministic. It's meant to be a research tool. So that led to the creation of what's called ROS 2. ROS 2, after an extensive shootout, settled on using DDS as its underlying framework for the data plumbing, essentially. The thinking being that if you're not spending time on the middleware, then you can spend more time on what's really important, or the value of the system is, and that's in the making better tools and better capabilities for autonomous systems. And so they use DDS. Coming from a supplier of DDS, I tend to look at it from the bottom up. What this means is that every ROS 2 application is a DDS application. Since it's built on the framework, so it makes it where all these ROS 2 applications, and I'm talking about everything, the modules, the packages, the tools, since they are DDS applications, they are enforced by the standard. They are interoperable with native DDS applications. So this is great news, where we've got this amazing ROS 2 tools, or ROS 2 ecosystem, and then there's a DDS ecosystem. But by recognizing that it's DDS in both cases, the size of the ecosystem, the number of tools and packages that you have available has just doubled or more. So you can freely intermix ROS 2 applications and DDS applications, and you have full access to both tools ecosystems. So an example of a hybrid system that's using both might look something like this. And the idea being that with ROS 2, ROS is intended primarily as a research tool. So there are things baked into the system like command line introspection and being able to change out the middleware at runtime, which all these things, what they do is they increase the code size and they add latency to the system. So that being said, though, there's a lot of great pre-written packages that are available in ROS. So as a guideline, if there are pre-written packages that are available in ROS, no sense in rewriting them. But if you have something that is safety critical or mission critical, or you need to run at absolute top speed, it's very simple and straightforward to implement it directly in DDS. And the nice part is then you've got this great tools ecosystem to help you get the applications up and running. Now we know we can do this because of the interoperability of DDS, and the way to start doing this is just to look at the data model within ROS 2. There are about 350 structure definitions to make all the data types in ROS 2, at least in the standard. You're free, of course, to make your own data types. RTI has accumulated in all of these structure definitions in IDL and XML format, which we use in our code generation equipment. So it's very straightforward to make applications that speak ROS 2. So these struct definitions or topics, they're used in ROS 2 in 4 different ways. And this is everything that ROS 2 does. All right, the first is messages. This is just pub/sub data topics. There are things called ROS 2 services, and that's like a request-reply pattern where you can ask something to do something. There's something called actions, which is a lot like services, but there's also a feedback message. So you can see things. It's also called objective state, but you can request something be done and also get feedback of it as it's happening. And then there's a global parameter system. One of the demo applications within ROS2 uses all four. So if you're ever curious about, okay, how do these things work, TurtleSim is an easy way to do it. And when you launch TurtleSim, though, it's kind of interesting, where it showcases the things that ROS can do, but it also shows some of the drawbacks of the implementation that was done with ROS. The first one that is unfortunately, I think, going to affect scalability with ROS2 is they made the decision to not use the DDS key system. Instead, they used topic names, sort of like a C++ name mangling, where the node and the application and the type of data it is all encoded in the topic name. So this makes for a very long topic list. When you launch TurtleSim, it makes more than a couple dozen topics. So I have a little decoder ring on here. There's to tell what type of topic it has, what type of purpose, whether it's a service or an action or a parameter or just a user message type. All right, pointing out one other thing that's within ROS2, and that's the RViz2 3D visualizer. It's a visualizer for lots of different types of sensor data. So in that regard, it's very convenient to have around, especially since it's a free resource. At RTI, we've gotten lots and lots of mileage out of it. So we're using it for things like LiDAR visibility, but also things that it wasn't necessarily intended for, like it can render STL files, which are sort of triangle-based representations of objects. And so here we've got the area around the Denver airport, and there's some planes that are rendered in STL, and in the upper left there, and using point clouds and the occupancy grid to just render an image, which looks kind of interesting. Okay. So getting started with Connext Pro. Now, my understanding is that students have not yet received Connext Pro. That's going to be happening shortly. There's an introduction letter. I'm not certain if it's been sent out yet, but it directs you to go to the free trial site for RTI. Normally there's a registration process, but we're sending you directly to the download page. So you'll download the executable or the installer for Windows, but it's also available for Mac OS and Linux. In the welcome email, there is a license file that allows this to run. So just copy that. When you do the installation, it opens up the launcher, and then you just point to the license file, and then you're done. Everything should work. What this will look like, when you launch the launcher, there are different tabs to launch different things. Admin Console is one. That's sort of in the mid-left here, but there are monitoring tools, command line tools, the services for doing things like recording DDS data streams and playing them back, doing a persistence service, and of course the code generation tools, which look like this. So Code Generator is a resource that's available. It's a command line utility that also has a graphical mode of operation. And in generating applications under Connext, this is assuming, and to build applications that use DDS is a capability that's being added to SCADE. But for handwriting code in your choice of language, you'll start with an IDL file that describes your topic types. Run that through the RTI code, DDS code generator, and that produces type support source code. It can also produce an example application that makes a publisher and a subscriber if you want, and even do the make files or Visual Studio project files. Run that through your tool chain with your added code, and it'll link with the DDS libraries, reference the quality of service, and you've got a DDS application. This can happen very quickly. One of the fun things to do with a new user with DDS is when you're talking with them, demonstrating the product, to on the fly just create an IDL file that, as you're talking about the data, say, yeah, would it look like this? And then within a minute, you've got applications built that speak that custom data type. So it's pretty cool. All right, a little bit more time on Admin Console. Again, this is your best friend in diagnosing DDS systems and getting high performance out of them. It shows you what all the topics are that are present on the system in every domain. The central display that has the boxes. I don't know if you can see my mouse on the screen. This is a topic called parameter events, and it shows that there's one publisher and one subscriber. You may notice that there are little yellow triangles next to most of the topics, and what Admin Console does is it immediately identifies when there's a problem. This is just a warning that says this is a publisher or subscriber only topic, meaning that there's half of a connection there. But by clicking on any of these, you can see what the discovered quality of service information is, find out what the data type is, and if there are any type of mismatches between them. For whatever reason it's rejecting a connection, it'll tell you right away what that problem is. DDS has an advantage where if there is a problem with a data type mismatch or a quality of service type mismatch, it'll reject the connection. So there's really no possibility that you can develop a product with a slight mismatch on something and then deploy it and have a problem in the field. It'll let you know right away, hey, there's a small problem, you need to fix it. And this is the tool to help you do it. What's also cool about Admin Console is more than just looking at topics, it can subscribe to topics. So you can do a sort of a deep packet inspection and see what the content is. In the right side of the screen, it's showing not only what the topic, user topic data types and values are, but it shows the value of a lot of the metadata like timestamps and strength and sequence numbers and unique identifiers that help the DDS system do what it does with the packages. You can also take that data and plot it to a log or even graphically plot it over time, which again is really convenient. Imagine having throttle, RPM speed, wheel speed, brake pressure, all plotted over time to see how the system is behaving dynamically. Now, since this is a network framework, Wireshark is another option for looking at the packets. Typically, we don't use Wireshark unless it's something that's like really deep, like there's, for whatever reason, there's a problem with discovery, or maybe it's a version incompatibility or something like that. This is getting very deep into the internals of DDS. All versions of Wireshark that are relatively recent within the last few years have a dissector for the protocol that is used by DDS. It's called RTPS, for real-time publish subscribe. And so you can do a much more deep inspection of the content rather than just looking at hex bytes. And you're actually looking at what each byte means, because RTI has contributed to the Wireshark effort, a RTPS packet dissector. And as you're getting further along, there's one more really useful tool, and it's called Monitor. And what this is we have in the RTI DDS libraries a really simple switch to enable monitoring support. And this exposes the internal buffer layers and the queue sizes, and if there's any missed deadlines or that sort of thing. Those are exposed as DDS topics, and the monitor is something that allows you to look at them in real time. So if you're really trying to reduce or increase the performance, reduce latency, reduce the code footprint or the memory footprint of your application, Monitor is the way to do it. Now, both Admin Console and Monitor have the capability of doing what's called a distributed logging. And they say not really a tool. What it is there are events that can happen in your application that can issue, if you enable logging, it can issue a logging packet. And these also can be user-defined events. So if you have a distributed system and there's some behavior happening, this is a way to facilitate what's happening in every node in real time, in order. It shows the logging messages. Essentially, it's like doing printf debugging, but it's doing it across a large system. So you know, it's a really nice way of having visibility in real time across your entire system. All right, one more thing, and that is RTI Connector. And I'm a big fan of RTI Connector. What this is, it's a freely downloadable way of getting DDS access using Python or JavaScript or Lua or Go. You know, there's a few other languages, but right now the mainline support is for Python and JavaScript. You can actually install them using pip for Python or npm for Node. But it makes it where you have access to your DDS topics to either publish or subscribe using Python scripts or using like Node.js to do things, you know, if you want to make a like a web view or a web control over your DDS system. Just for a couple of examples, you know, this is another one that I really like it. There's, especially with the Python one, it's very easy to get things running quickly. For instance, on the right, this is a point cloud viewed in spheres. I made something that kind of rotates and swirls. It took about 5 minutes to do that. This is rendered with RViz. On the left is one that was done with the Node version of Connector. And this was actually using discovered information on it was a power grid control system. And it was a way of clicking on individual elements, which would launch then a control instance where I could turn items on or off using nothing but discovered information. So, you know, talk about having a really simple way to make an HMI or, you know, an interface to control a system. This was one that it was no code written to actually make the elements. So that was kind of cool. All right, and finally, there's another resource is the RTI community website, which is community.rti.com. And we've actually made a special page available just for this Indy Autonomous Challenge. There is a link for it near the top. This is in actually the ROS 2 integration, but we will likely have a link from the top. But that's something that I'll have a resource slide available coming up next that has a link directly to this. The community site is a great place to get best practices, how-to questions answered. There's, you know, a community forum. That's in addition to the support channels, but links to videos, all the documentation is here. If you ever really want to dive much more deeply or get quick answers on how to use DDS to its best effect, this is a great place to start. And finally, for a resource page, here is a number of links that are available. You know, again, the free download, community site, where to get Connector, and then some resources that are available for the IDL and XML for either automotive use or ROS interop use. And so with that, that concludes the end of my slides. You guys were great listeners. It went a bit fast.